Okay, so for quicksort, the best case and worst case are going to depend on the choice of your pivot. So the criteria for a good pivot is going to be when it divides your array into two subarrays of equal size, of roughly equal size. And so that's going to happen when you choose the median as your pivot, whereas a bad pivot is going to be when you choose one of the values at the extreme endpoints of your range. So either the smallest element or the largest element, and that's going to result in subarrays of size n minus 1, right? Because everything is either going to be smaller than or larger than that pivot. So let's examine the worst case runtime first. So we have n, and that's going to recurse on an array of size n minus 1, then n minus 2, and that's going to get down to 1. That's going to be of height n, right? So remember the recursion formula, I equals 0 to height, the branching factor to the I, and then the amount of work per node. So in our case, height is going to be n, but since we're indexing from 0, let's have it be n minus 1. And the branching factor is 1 to the I because we're only calling it a one subarray, right? Everything is to the left or to the right of the pivot. The amount of work per node is going to be linear in terms of that node input size. And the reason for being linear is we are looking at every single element within that subarray to see whether it's less than, equal to, or greater than the pivot. And so that's going to be n minus I in terms of the input size at each level. And so there are two ways of solving this. One way, I'm going to show both ways, but the first way is by actually just plugging in I into this expression. So if we start at I equals 0 and all the way to I equals n minus 1, this is going to be n plus n minus 1 plus etc. to 1, right? And so we know from previous experiences that this is going to be equal to n squared. Another way that you can solve it is by actually putting it in terms of two summations. And so this is going to be I equals 0 to n minus 1 of n minus I equals 0 to n minus 1 of I. The first expression is just going to be n times n, okay? N times n. And the second expression is going to be 0 plus 1 plus all the way to n minus 1. And in fact, if we just say that it's from 1 to n, right? So 1 plus 2 plus all the way to n, this is equal to n times n minus 1 over 2, precisely. We always approximate it as just n squared, but if we look at it really precisely, it's n times n minus 1 over 2, which means that if we expand this out, n squared minus n times n minus 1 over 2, and we have it common denominator, right? Or let's say, let me do a simpler way. So we can just simplify the second term to be approximately n squared over 2, right? In fact, it's overestimating, which is good. Which means that we're going to be left with n squared over 2, which in the long-term asymptotic analysis, it's really just going to be equal to n squared. So either way, we get n squared for worst case. Now for best case, that's when our pivot is going to be the median, right? And so that's going to be when we have n going into two input arrays of size n over 2 each. And these are going to branch off into size n over 4 each, and etc. And so again, we can apply the same recursion formula to each of these, to this entire best case scenario. So I equals 0, height is now going to be log n, and then the branching factor is going to be 2. So now we have 2 to the I, and the amount of work per node is again linear, but now the input size is going to be n over 2 to the I. And so if we look at this, this nicely cancels out, right? This 2 to the I in the denominator. So now we get I equals 0 log n of n, which is just n log n. And in fact, this is the best case.